Hello students. So in the last lecture we had discussed about the definition of uniform continuity. Now and some examples of the uniform continuity. Now in this lecture we start with the theorem that relates the uniform continuity with continuity, that is which one is implies to another one, that is if the function is uniformly continuous then can we say that the f is continuous or vice versa. So let us see the theorem. The statement of that theorem is what is that theorem? Let x d1 let x d1 and y d2 be any two metric spaces and f from x to y be a uniformly continuous function. F from x to y be a uniformly continuous function, then f is continuous on x. Then f is continuous on x. So if we have the two metric spaces xd1 and y d2 be any two metric spaces and f from x to y be a uniformly continuous function, then f is continuous. म्हणजे जर फंक्शन युनिफॉर्मली कंटिन्युअस असेल तर आपण काय म्हणतो की ते फंक्शन जे आहे ते कंटिन्युअस आहे. ओके, दॅट इज युनिफॉर्मली कंटिन्युटी इम्प्लाइज कंटिन्युटी. नाउ वी हॅव द प्रूफ. Let p belongs to capital X and epsilon greater than 0 be given. That is, we have a point and epsilon are given. Also we have f is uniformly continuous. Also we have f is uniformly continuous. This implies that there exists delta greater than 0. This implies there exists delta greater than 0 such that mod of x minus y is less than delta. This implies that mod of f of x minus f of y less than epsilon for all x comma y belongs to capital X. Now taking y is equal to p, we get mod of x minus y is less than delta. This implies that mod of x minus p, here we have taken y is equal to, this implies mod of f of x minus f of p less than epsilon. This implies that f is continuous at p and p belongs to capital X is an arbitrary point. This implies that f is continuous on x. So this theorem gives the relation that every uniformly continuous function is continuous. Every uniformly continuous function is continuous. Also, we have in the last lecture we had proved that if f and g are continuous function, then f plus minus g alpha into f are continuous function. But we had not discussion about what is the nature of f into g. Either f into g is continuous or uniformly continuous or not. Now here is a theorem that says that f into g is uniformly continuous under some certain conditions, so the statement is, let xd be any metric space and f comma g from x to r be uniformly continuous. Suppose if f and g are bounded functions, then f into g is uniformly continuous, isn't it? So what is the statement? F into g is uniformly continuous provided f into g is uniformly continuous provided the condition that f and g are bounded function. Under the condition that f and g are bounded functions. Now the proof. We have f and g are bounded functions. We have f and g are bounded functions. This implies that there exists m greater than 0 such that mod of f of x is strictly less than m and mod of g of x is strictly less than m for all x. Also f and g are uniformly continuous. F and g are uniformly continuous functions. Also f and g are uniformly continuous functions. This implies that there exists delta 1 greater than 0 and delta 2 greater than 0 such that d of x comma y is less than delta 1 implies mod f of x minus f of y less than epsilon upon 2m because f is uniformly continuous. Similarly, d of x comma y is strictly less than delta 2 implies mod of g of x minus g of y is less than epsilon upon 2m. So for given epsilon upon 2m we can always find delta 1 and delta 2 such that these two conditions get satisfies. Let delta is equal to minimum of delta 1 comma delta 2, then let delta is equal to minimum of delta 1 comma delta 2, then d of x comma y is strictly less than delta implies mod of f of x minus f of y less than epsilon upon 2m and mod of g of x minus g of y is less than epsilon upon 2m. Now consider f into g of x minus f into g of y is equal to modulus of f of x into g of x minus f of y into g of y. F of x into g of x minus f of y into g of y, which is equal to modulus of f of x into g of x minus f of x into g of y plus f of x into g of y minus f of y into g of y. That is adding and subtracting the term f of x into g of y, which is less than or equal to mod of f of x into g of x minus g of y plus here which term is common, f of x f of y, g of x g of y, f of x into g of y. Now here g of y is the term common, so f of x minus f of y, which is less than or equal to m into this term is less than epsilon upon 2m, which is strictly less than epsilon upon 2m plus mod of g of y is less than m, and this term is less than epsilon upon 2m, so this m get cancel, epsilon upon 2m and epsilon upon 2m will be epsilon. This implies that f into g is uniformly continuous. This implies that f into g is uniformly continuous. Now we have the next theorem which relates the uniform continuity and a Cauchy sequence. Uniform continuity and a Cauchy sequence. So that theorem says that let x d1 and y d2 be any two metric spaces and f from x to y be uniformly continuous, let xn be a Cauchy sequence, let xn be a Cauchy sequence in capital X, then f of xn is also a Cauchy sequence. Then f of xn is also a Cauchy sequence. That is, for the two metric spaces x d1 and y d2, if f is uniformly continuous, then Cauchy sequence is preserved under that mapping. That is, Cauchy sequence is preserved under uniformly continuous function. That is, if xn is a Cauchy sequence, then f of xn is also a Cauchy sequence. Now we have to prove that f of xn is a Cauchy sequence. For that, let epsilon greater than 0 be given. Let epsilon greater than 0 be given and xn be a Cauchy f of xn be a xn be a Cauchy sequence, and f from x to y is uniformly continuous function. This implies there exists delta greater than 0 such that d1 of x comma y is less than delta, implies that d2 of f of x comma f of y is less than epsilon. Now here it gives the relation between the 2 points in domain, and we have to assume that xn is Cauchy sequence. So corresponding to and Cauchy sequence xn in x, so corresponding to this delta corresponding to this delta greater than 0, there exists n naught belongs to capital N such that d1 of xn comma xm is less than epsilon for all n greater than or equal to n naught. But whenever this happens, less than delta, whenever this happens, using this equation star, we have d2 of f of xn minus f of xm comma f of xm is less than epsilon for all n greater than or equal to n greater than m greater than or equal to n naught. Using star, and it shows that the sequence f of xn is Cauchy sequence. It shows that f of xn is Cauchy sequence.